Alrighty. I believe we are recording. So I'm using the same tool that I normally use in class, just so that I'm not going to be surprised again because I have not used OBS for a while and I forgot to click the button. So I'm just going to use Zoom for recording, and I am not expecting anyone to join the Zoom session today simply because the lecture is supposed to happen at noontime. On the other hand, if someone, is to request to join me during this supposedly just a recording of a lecture, they're welcome to. All right, so let's go ahead and get started here. So we are now in discrete probability. We are basically done with counting. We got a few more concepts that we probably should talk about, such as how to generate all the combinations when we have an experiment with trials without replacement. So the concept of with and without replacement, the concept of trial, the concept of experiment is already discussed in this particular module. So we're going to move on to discrete probability in today's lecture, and I have it up on one of my, right there. So this is already here, and Joplin already has the content that I worked on yesterday, simply because to you, this is all new. To me, this is not new at all because I worked on this yesterday, except I forgot to turn on the recording. Forgot to click start recording. So this is all new to you, but it's not new to me. Unfortunately, I already worked on this yesterday, but that's okay. We'll go ahead and start from the beginning. All right, so let me switch back to the lecture content. The first part, okay, that talks about what is an outcome, what is an event, and so on. We talked about all of those already, so I'm not going to spend too much time to talk about this. The only part that we have not talked about is what is an event. So an event is actually a set, okay? So an event is basically a set, and it is a subset of omega. And in this case, omega is the outcome set of the experiment itself. Every single way that can end up as a outcome, those are all elements within omega. So an event is basically constructed based on what you're trying to get to. So in a Powerball lottery, a particular event, which is a set, may include all the tickets that win a particular prize. Such as if there's a prize that kind of get you $3, then we can look at all the tickets that can give you a return of $3 as the event set. And obviously, that is going to be a subset of all the possible tickets in Lotto. And in that particular case, big omega is going to be a set consisting with all the possible tickets. So when we talk about probability in general, it is the ratio between the cardinality of the event set versus the cardinality of big omega. In other words, we are looking at how many of the outcomes that are possible are the ones that we're interested in, and assuming probability distribution is otherwise the same, then this will give us a realistic view of the actual probability. Example one, moving on to example one. This is something that we talked about in previous classes. In fact, it's one of the first problems that we talked about in terms of discrete probability. It's called the birthday problem. So we talked about this already, so I'm going to skip this part here, but you should not, okay, because you should read this entire section and make sure that you understand this particular section, because we talked about this in class already. So what we'll do today is we are going to start with coin tossing. So coin tossing is interesting because, first of all, it is not without replacement. So in other words, it is with replacement. Just because one particular coin toss ends up with heads first, doesn't mean that next one cannot be heads first. So that means the trial outcomes would be the same for all the trials. We are not taking away possible choices from future trials just because an earlier trial ends up with a particular outcome. So in this particular example, I'm asking if I were to toss a coin 5 times, what are the chances that we end up with 3 heads and 2 tails? So the first thing we need to do is to make a few assumptions. So at first, we are going to assume the coin is not loaded. So that means the probability of landing on the head and the probability of landing on the tail are even. In other words, they are both 50% or 0.5 exactly. So now the question is, how do we compute this? So we'll start with big omega. In other words, we'll start with asking the question of how many ways can we, what are all the possible outcomes for tossing a coin 5 times? So that's the first question. And to answer the question, I have actually prepared a graph, which is not showing right now because I had to stop doing it. So let me set up the tool to show that first. Oops, this is the wrong window. I just grabbed the wrong one. This is the correct one. There we go. All right, so don't mind about this part first. What I will do is I'm going to go back to the beginning of Zerno. Basically, it's just a previous page. So, well, this may work, but I think I want to do it in a slightly different way. In other words, I want to do this in a way that really kind of shows the outcomes. So let me erase this page first, delete page. There we go. And then we'll go ahead and insert a page before. There we go. And then I need to rearrange my computer a little bit. And gosh, I forgot to put my stylus back. All right, so that is not going to work. But that's okay. I got another way to show this, which is using a spreadsheet. See, if one way doesn't work, there's always another way. So I can do this in a slightly different way. And let me close that window first, because I won't need it anymore because I just forgot my stylus in my office at home. I need to put a tether on my stylus so this way I don't lose things. So anyway, what I'll do, I am going to put this in the shared folder for this class. So let me go back to here and then go to shared. And then from here, I will create a new spreadsheet that will explain the possible outcomes. All right, there we go. And I would name the spreadsheet after today's date, which is 2023, April 12th. There we go. All right, so we are looking at 5 coin tosses. Okay, so we'll have the first toss, the second toss, the third, the fourth, and then finally the 5th. So these are basically the coin tosses. And for this one to work properly, I need to zoom out, actually not to zoom in, but to zoom out. So we'll try to get this more visible later on. So with the first try, okay, it can turn out as head or tail. So instead of just saying head or tail once, I am going to specify the head like 16 times and then specify the tail also 16 times. The reason why I do that is going to be clear later on, but right now we'll just go ahead and say that. So I'll have head, 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 just repeat it 16 times, which is a chore. Okay, so what I'll do instead is I am going to use the row number to help determine what letter I should use here. So I'm going to use an Excel function or Excel formula to do this. All right, so equal starts a Excel formula, and then row number is just row open and close paren. So now I need to use this to inform me, what letter is supposed to go here. So if you have taken CISP440 and understand base conversion, this is basically base conversion. I'm trying to compute digit 4 of a binary number. But before we do that, we have to subtract 2 from the row number so that we end up with a number that is starting with 0 and move on later after that. So now we have 0, and then we have to figure out what power of 2 that we need to divide this by. So we divide it by the power of 2, and the power is going to be, this is supposed to be 2 to the power of 4, and this one here is supposed to be 2 to the power of 0. So we have 0, 1, 2, 3, 4. So that means the power is really 5 minus the column number, because column numbers are 1-oriented, which means your column A is known as column 1. So I need to subtract that from 5 in order to end up with the 4. Okay, so now with this number, it is not always an integer. So what we'll do is we're going to take the floor of this particular division. So we close the floor, and now we end up with an integer. But this integer is not always necessarily 0 or 1. So we'll do a mod of the entire thing. So we'll mod this number by 2, which means we are taking the remainder of that number and of that number divided by 2, which now has to be a 0 or 1. And we are now going to say if this number is a 0, then we want to use head. And I mean, this part here is really arbitrary, which one corresponds to a head, which one corresponds to a tail. So I'm just basically saying 0 corresponds to a head and 1 corresponds to a tail. So now I have this equation. Yes, it doesn't work. Let's find out why. Formula parse error. So that means I probably misplaced the commas somewhere, or the equal to. It's not, this is not how it's supposed to work. So let me just double check. This is divided by the power, and we take the floor of that, and then we mod that the floor of the division by 2, and we compare that to 0. And if it is true, we have head. So I think it has to do with double quotes versus single quotes. I can never really quite remember. So that looks about right, because the color coding tells me that this is now correct. Okay, there we go. So the magical thing about using a formula approach to populate the, this is basically a truth table, but the magical property of this is now I can extend it, to the 5 cells over here. And then I can extend it all the way down to row, I think it's 33. Okay, maybe. Yeah, 33. So now we have basically a truth table, but instead of looking at this as a truth table or a table of binary numbers, we can basically just say, oh, so this is the experiment outcome of all heads in the experiment. This one is one of the outcomes where we have 4 heads and 1 tail. This is another case where we have 4 heads and 1 tail. This is one of the cases of 3 heads and 2 tails, and so on. So, so now all we need to do is to figure out which ones are the ones that end up with. Okay, first of all, how many are those? How many outcomes do we have? Possible, how many, okay, let me rephrase that. How many possible outcomes do we end up with in terms of, tossing a coin 5 times? And the answer would be counting from this row all the way down to the last row over here. And that there are 32 of these. So the question is, why are there 32 of those? That's because, the first one has 2 choices. It can be head or tail. So if you are to draw a tree, the first level of the tree, starting from the root node, has a fan out of 2 of head and tail. For each node of the first level, It also has a subtree. It also has a fan out ratio of 2, which is also head and tail. Same over here. We split again. Once again, the fan out ratio is 2. Once again, we have the fan out ratio of 2. Once again, we have the fan out of ratio of 2. So we end up with 2 times 2 times 2 times 2 times 2, otherwise known as 2 to the power of 5, which is 32. So we have 32 possible outcomes, which means the cardinality of omega is 32. So now we ask, what about our event set? So in this case, the event set would include this as an element, because the question that we are asking is, what are the chances that we end up with 3 heads and 2 tails? So this is one, and I am going to slightly color this just so that we know, we can count this a little bit more easily. The next one is this one here. You can see this one also has 3 heads and 2 tails. So we'll go ahead and highlight this one. And then we move on. There's this one, which also has 3 heads and 2 tails. So we are just, sequentially, manually, in this case, going through the whole table, which is very tedious, okay, but it is doable. This one also has 3 heads and 2 tails. And there are ways to kind of automate this, because what we can do is we can count. There's a function called COUNTIF. So let's do it that way, okay? Because in addition to teaching you concepts in CISP440 in this case, I can also teach you how to use a spreadsheet, and this is really kind of cool. So we can use a function or a formula called COUNTIF. So with COUNTIF, you basically specify a range first of, okay, what is the potential range of things that we are counting? And then you specify a criteria. In this case, the criteria is we want to count the number of heads. So we have to specify it equals to h, and I think that will match the h, within this part. And it's 5. That is correct. Okay, so there are 5 heads in this case. So if I were to expand this all the way down to the bottom, and you can see how it is all correct. The last row, they're all tails, and therefore we have 0 heads. And this one has 1 head, this one has 1 head, this one has 2 heads, and so on. So now we can do a really quick filter and see which one is a 3. So there are a few ways to do this again. So you can now say, oh, I only want to indicate whether this is exactly 3. Okay, so you can just do a comparison. And then we change, once again, we propagate this equation. There's a way that you can use an array formula, and you can just basically specify the rule just once, and it'll be done. So now it becomes a lot easier to see which one is true and which one is false. And to visually make this a little bit easier, we can now go to Format, and we can go for conditional formatting. And in conditional formatting, you can basically specify, I want to use a single color applying to the cells that we have just specified here. And we can now specify when the color is supposed to be, when to use a color. So we can now specify is equal to true. And that's it. So this makes it very easy to count the cells or the rows where we have exactly 3 heads and 2 tails. So we can do some counting here. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There are 10 of these. Now, if you don't trust me, you can also specify equals to COUNTIF. And now we specify, this range of cells, like so. And then we specify that we want these to be true. And there are exactly 10 of them. So that means the probability of ending up with 3 heads and 2 tails, regardless of the position in a game that involves an experiment that involves 5 coin tosses is 10 divided by 32. So if I really want to do the actual calculation, it is 10 divided by 32, and it is 31.25%. That's it, right? So it would appear that it is not difficult to figure out by hand, but figuring out things by hand is not exactly the best way of doing things because it is time consuming, it is very tedious, and sometimes it just doesn't work for various reasons. So now, and also the other thing is we are also making an assumption that the chances of landing on the head and the chance of landing on the tail are indeed the same in this case. So what are we going to do here? Because this is, I mean, this works, but it is not generally very useful. So we'll just throw the first wrench into this entire thing, which is to say, oh, let's not make that assumption. Let's not make the assumption that the chances of landing on the head and the chances of landing on the tail are the same. Okay, so we're just removing that assumption. So from now on, we are going to, and let me switch back to Joplin because this is already in Joplin. So I have already gone over all of this stuff here, and we are now ending with this. Oh, actually, we're not quite done with all of that. All right, so the counting, okay, so let's look at the manual counting example first. So there are 10 of those. The question is, can we look at this problem in a slightly different way? In other words, let me switch back to Joplin. Can we look at it this way? In order to express a tuple of head, tail, head, head, tail, which means the first trial ends up with a head, the second trial ends up with a tail, the third trial ends up with a head again, and so on. Can we encode this in a different way of 0, 2, 3? So you might be asking, what does 0, 2, 3 have anything to do with the 5 tuple of head, tail, head, head, tail? Well, as it turns out, this particular set, okay, this is not a tuple, this is a set. So as it turns out, this set only contains the index 0-oriented of the positions where we end up with a head. So this is position 0, this is position 2, and this is position 3. 0, 2, 3. So why is this a set then? Why is it not a tuple? Because how we order 0, 2, and 3 does not matter, because I just need to know, is position 0 ahead? Is position 2 ahead? Is position 3 ahead? Is position 1 ahead? It is not, because 1 is missing from this set. Is position 4 ahead? It is not, because 4 is also missing from this set. In other words, it is a membership issue. It is not, it has no positional sensitivity. We don't care about the positioning of 0, 2, 3 within the set, because the question that we're going to ask is not when, how, or the positioning of the 0. We're just asking, is 0 in this set or not? And as a result, ordering is not important. We are looking at combination. So once we look at a particular trial out of tossing 5 coins in this particular manner and encode the result as a set, which is basically the same thing as saying, hey, here's a bag with the numbers 0, 1, 2, 3, 4, and just go ahead and draw 3 numbers out of the bag, and those 3 numbers will correspond to the 3 positions within the 5 tuple where we are going to find a head instead of a tail. You go like, and we want to count the number of ways that we can draw 3 numbers out of the 5 in the bag without replacement, because once you draw 0 out of the bag, you cannot put it back in and draw 0 again. Then you go like, didn't we solve that kind of problem before? Because I vaguely remember that we talked about permutations versus combination. They all have to do with picking something from a bag in random without replacement. Whatever you take out of the bag, you don't put it back in the bag for further trials. And then we put all of those things either into another bag or we put it into a tube. In this case, we're putting it in a bag. And if that is what this is reminding you, great. Okay, so that means you're already associating these newer concepts with things that we have learned already. So in this case, if we're interested in the number of 3 heads and 2 tails from 5 trials, this is the event set or the cardinality of the event set. It turns out to be the same thing as 5 choose 3. This is another way to write out 5 choose 3. So if you ask mathematicians or statisticians, there we go. I'm sorry because my pronunciation is always kind of a little bit wonky. I have to visualize the word and then break it apart and then pronounce it. So if you ask those people, the mathematicians and also the statisticians, they would use this notation. But if you ask someone who knows a lot about spreadsheets like myself, I'm going to say, oh, this is just combin, okay? The number of combinations of 5 choose 3. So according to the definition of 5 choose 3 or the combination of 5 choosing 3, it is 5 factorial divided by 5 minus 3, which is 2 factorial. And we also have 3 factorial in the denominator. 5 factorial itself is 120, 2 factorial is 2, and then 3 factorial is a 6, and we end up with a value of 10. Didn't we get to 10 before? I mean, let's check it. So we got to 10 over here, right here. So the way we did the manual counting is consistent with the mathematical way to come up with the number of ways to end up with 3 heads in 5 coin tosses. Great. So now we're looking at just an enumeration of the 5, which is actually encoded here for every row that has a true, which is highlighted. Those are corresponding to the 5 ways of ending up with 3 heads in 5 coin tosses. And just as I explained it earlier, the chances of ending up with 3 heads and 2 tails, oh, this is wrong. Now I caught it. Now I'm catching this. It's supposed to be 3 heads and 2 tails from 5 coin tosses is going to be 10 divided by 32. And we worked this out a little bit earlier. It turns out to be what, 8 point, nope, take it back. I take it back. It turns out to be 31.25% or 0.3125, if you don't want to look at it as a percentage. So now we're starting to look into this and go like, what if the chances of landing on the head is represented by P and it doesn't have to be 0.5 now. And then the chances of landing on the tail is just going to be 1 minus P, but we'll call that Q just so that we don't have to write 1 minus P all over the place. So what about that? So the way we understand the probability in this case, when the chances of landing on the head and the chances of landing on the tail are not 50-50, all we have to do is to multiply the 10 by P to the power of 3 and Q to the power of 2. Now, why is that the case? Well, to understand that, we can also just go back and look at the spreadsheet. Because in all of these cases, the first one, in order to end as a head, that's P. That is P. That is P. This is tail. This is Q, and this is Q. So that means we are multiplying P to the power of 3 by Q to the power of 2. So that's 1. But when you look at any one of these, okay, let's look at this one here. This is P because we ended up with a head. The chances of landing on the head is P. The chances of landing on the tail is Q. So we have P times Q times P times Q times P. But after you do the associative law thing, it also ends up as P to the power of 3 times Q to the power of 2. We can look at another example. Let's look at this one here. It is Q times P times P times Q times P. And once you do some algebra stuff, you're moving things around because of the associative law of multiplication. We also end up with P to the power of 3 times Q to the power of 2. So every single one of these rows, okay, this row, this row, this row, and so on, every single one of these rows ends up with a probability of p to the power of 3 times 2 to the power of 2, and then there are 10 of these. So we have to add up all 10 because in the end, we are just we are interested in the probability of ending up with 3 heads and 2 tails, and the positioning is not important. And that is why the probability of 3 heads and 2 tails is also just known as 10 times p to the power of 3 and q to the power of 2. Now, how does this relate to this over here? Well, this is based on the assumption that the chances of landing on the head and the chances of landing on the tail are exactly the same, which means P is 0.5 and Q is also 0.5. So if you ask what is 10 times 0.5 to the power of 3 times 0.5 to the power of 2, it is exactly the same as 10 times 1 divided by 32, because if P is 0.5 and Q is 0.5, they are both known as just 1/2, right? So what happens when you have 1/2 to the power of 5? It becomes 1 divided by 32, because 32 is 2 to the power of 5. So that means this is the more general way to describe the probability, because it works also in the case that P and Q are both 0.5. But it also works when P and Q are not even. You can say, oh, if one is 0.7, the other one is 0.3, this general equation also works. So now we are getting into what we call a binomial distribution. And you look at all of the stuff we have done. Okay, so let's take a look at this thing here. We'll take a look at this thing over here, and even this thing over here. None of that looks like a binomial. So the question is, why are we talking about binomial distribution? Well, we can now take a look at, now we are re-expressing the probability as the terms after the expansion of a binomial to the power of something. So I'm missing one over here. In fact, I'm missing 2 of them. Okay, so we have p plus q to the power of 0. Okay, and what is that? Oh, that's just 1, because anything to the power of 0 is 1. There we go. So this is corresponding to, here's a coin, but don't toss it, because we have to the power 0 here. So that means we're not tossing the coin. And then we're asking, what is the probability that we end up with nothing after the coin toss? And the chance is 100%, because we did not do a single thing. So the next question is, what about tossing the coin just once? Well, then we get just p plus q. Okay, but this p here, I mean, this looks really stupid, right? Anything to the power of 1 is that something, but the end result here has meaning, because this p is corresponding to, oh, so what are the chances of having one single head and one single tail? The chances of landing on the head after one single coin toss is just p. The chances of landing on the tail after one coin toss is q. You go like, yeah, so what? Because this is exactly how p and q are defined. All right, well, just stay with me a little bit here. What if we are to toss the coin twice? Okay, what's going to happen? Well, in that case, the chances of landing on the head twice, basically 2 times out of 2 times, is p squared, because the first time it has a chance of p, the second time it also has a chance of p, so as a result it's p squared. But then the chances of landing on the head and also landing on the tail once each is 2 times pq, because we can land on the head first, then we land on the tail, which means we have p times q. But we can also land on the tail first, and then we land on the head, which is q times p. But because of the associative law in multiplication, we can exchange the position, so we just end up with 2 times p times q. And then this is representing the chances of landing on the tail both times, since the chances of landing on the tail twice of those things happening is going to be the chance of q squared. So now we can expand, p plus q to the power 3, which is basically corresponding to tossing the coin 3 times, tossing the coin 4 times, and tossing the coin 5 times. And I'm fairly sure that all of you are familiar all the way at least up to here, but this part here is just tedious work, right? I mean, if you know how to get to the cube of the binomial distribution expansion, you can always work it up to higher numbers. It's just a whole lot more tedious. But look at this here. When we are interested in 3 heads and 2 tails, the coefficient that we multiply to that term is exactly 10. So I hope now you're starting to see, okay, so we are indeed looking at the expansion of a binomial expression, and this is also why it is called the binomial distribution. So getting back to the notes, let's check out, where in the notes we are talking about this. Okay, this is old stuff already. Let me get rid of the stuff that is irrelevant at this point. All right, so here we are now going to talk about Pascal's identity. So this is, it looks like a segue, but it really is, important. So we're going to use Pascal's identity as a mechanism to help us prove something that is far more useful. So we look at this math here. It is, it's just a big chunk of mumbo jumbo, right? So we want to kind of take a closer look at this and understand what is going on, okay? This is mostly algebra with a trick within the whole thing. So I'll tell you what the trick is. It is called, this is what I call, okay? This is definitely just text term and not a general term used by mathematicians or computer scientists or whatnot. So I call this the accordion effect of factorial. And accordion, so let's check out how accordion is supposed to be spelled. There we go. Accordion as opposed to accordion. All right. No, that is not my fetal what's that? Feeble attempt of making things sound like French. And where's my cursor? Oh no. Oh, there we go. It's back. All right. All right. So what am I talking about here? Well, what I'm talking about here is n factorial can be re-expressed as n times n minus 1 factorial. That's what I'm talking about, the accordion effect. So, okay, so that sounds pretty reasonable, right? Assuming that n is at least 1. Okay, so let me quantify this part here. So we'll say for all n that is an integer and is greater than 1. So we'll say n is in z, which is the symbol for integers. And we also need a guard condition here because we don't want to deal with n being negative, right? So we have to say that if n is if n is greater than 0, then the rest applies. Right arrow, and then put an extra pair of parentheses around this. All right, so that seems correct. I'm just matching the number of parentheses. Okay, so that's basically it's what I would call the accordion effect of factorial. For any integer n that is greater than 0, which basically means it is at least 1, n factorial can be re-expressed as n times n minus 1 factorial. You go like, yeah, okay, that seems to make sense because 5 times 4 times 3 times 2 times 1, otherwise known as 5 factorial, is 5 times 4 factorial because 4 factorial itself is 4 times 3 times 2 times 1. All right, seems to make sense. Okay. So given this accordion accordion effect in factorials, let's go back to the proof that we were looking at earlier, and then we'll find out what's happening here. To go from n choose k to n factorial divided by k factorial times n minus k factorial, that's definition, okay? By now we should know this already. The number of combinations of choosing k out of n items without replacement is n factorial divided by k factorial times n minus k factorial in the denominator here. So using the same definition, n choose k minus 1 becomes this mess over here. That's what line 1 is trying to express. Line 1, to go to line 2, I'm simply rewriting n minus open paren k minus 1 close paren as n minus k in parentheses plus 1. Because this negative and this negative here turns into this positive here, and the k has an implicit positive here, but it's inside a subtraction, and that's why it is remaining as a subtraction here. So this is just algebra. From here to here, I'm using the accordion effect already. So I'm asking, what happens if I multiply the numerator by k? That's not exciting, because if you were to multiply n factorial by k, you just end up with n factorial times k. Not exciting at all. But in order to preserve the value, I also have to multiply the denominator by k. That is when I use the accordion effect, because k times, in parentheses, k minus 1 factorial is just k factorial. So that is when things get a little bit interesting, because now I can say, okay, so I can now start to unify the two denominators. I got one already. This one has got k factorial to begin with. This one has k minus 1 factorial to begin with. But guess what? I turned that k minus 1 factorial into k factorial by making the numerator look a little bit uglier. Okay, so that's one. And then I look at this thing here and go like, I wonder what happens if I were to divide both the numerator and the denominator by n minus k plus 1. So once again, I'm using the accordion effect of factorial and say, hey, if you divide n minus k plus 1 factorial by n minus k plus 1, you just end up with n minus k. That is also a use of the accordion effect. But then I also have to remember to divide both the numerator and the denominator by n minus k plus 1. So that's why the numerator looks uglier now. But one thing I have achieved at this point is the two sides of this addition, they both have the denominator of k factorial times n minus k factorial. It's just that the numerator looks ugly. So now I want to make the numerator to look also more alike to each other. So now I ask, well, what if I were to multiply n factorial by 1, except that 1 is expressed as n minus k plus 1 divided by n minus k plus 1? You go like, yeah, that's totally legitimate, but it does make this numerator, which looks really clean because it's just n factorial, to look like, wow, that is, that doesn't look good, right? It's ugly. But what I have also effectively done at this point is, if you just look at the numerator of the two sides of this particular addition, they both have the same denominator now. So that means I can now really just kind of dissolve, this particular addition or I can say I can move it up all the way to the numerator of both sides of the original addition. All right, so given that, I just end up with this expression here because they all have the same denominator. So now I look at this sub-expression here and go like, okay, let's do distribution. So if you are to apply distribution, we can once again use the accordion effect of factorial. So the n factorial times n plus 1 becomes n plus 1, the whole thing factorial. And then we look at n factorial times k, you go like, there's no way we can really simplify that. But it has a negative here because of the subtraction of k. And then we have this extra n factorial times k, which came from all the way here, that is standing out by itself. In addition to that, I'm also combining the division by n minus k plus 1 of the numerator, and I just move this division all the way down to the denominator itself. In other words, I'm multiplying this term to the denominator of the entire thing. So now we have k factorial times n minus k factorial, which is coming from here. But we also have the additional term of n minus k plus 1, which is coming from here. So now we just do some math here. Okay, these two cancel out. We end up with n plus 1 factorial, n plus 1, the whole thing factorial. And then we look at this part here and go like, we can apply the accordion effect of factorial again, because n minus k factorial times n minus k plus 1 is just n minus k plus 1, the whole thing factorial. So we have just one little part here. This is really just eye candy, because once we have n minus k plus 1, I can rearrange the things a little bit. So I can just rearrange the positioning of the plus 1 and the positioning of minus k, and just add some unnecessary parentheses around, so that n minus k plus 1 becomes n plus 1, the whole thing, minus k. The factorial operator still has to be applied, but this is the format of n plus 1 choose k. So this is the entire proof of the Pascal's identity. Now the question is this the only way to prove Pascal's identity? I don't know. I have a strong suspicion that there may be some other proofs, possibly simpler compared to the one that I show you here, but this is the one that I worked out. So this is the one that I'm showing you. All right, so what do we do next? I'm looking at the time because I do have a meeting. I have to be on the interview panel at 10 o'clock. So I have to be making sure that I'm not missing that. All right, so down below here, what are we talking about? So now we want to talk about the the binomial theorem. Okay, this is called the binomial theorem. The theorem is quantified. It basically says for every natural number n, p plus q to the power of n can be expressed as a sigma or a summation, where I as an index variable goes from 0 to n. And in each term that we're adding in the sigma is n choose I times p to the power of I times q to the power of n minus I. This is the binomial theorem. And the proof of the binomial theorem is this is where we introduce another proof technique. We have already talked about proof by contradiction. Now we're going to talk about proof by induction. Proof by induction is also very powerful as a proof technique, and it applies to a lot of proof that you may need to do in computer science. Now, when you work as a software engineer, do you have to prove theorems? The answer is, the answer is a little complicated. The answer is, yes, you're supposed to, but most likely you're not going to. That's got to be the answer, okay? I have to be honest. The reason why the answer is supposed to be you're supposed to is because proof by induction is a really good way to prove that your program, that your code is correct. Once and for all, you don't have to throw test cases at it. You basically just mathematically prove that this particular algorithm is implemented correctly. If this is the assumption of the input, then we can conclude once and for all that the outcome of applying this algorithm is going to match what it's supposed to do. But are you actually going to do that? Okay, this is also known as program verification. Chances are you are not going to do it for a few reasons. Reason number one is most people do not like math, and most people do not like to prove stuff, so they don't want to do it. But that means, well, what if your boss is telling you to do it? Well, the thing is, your boss may not ask you to do it either. Because if you're not working for critical applications like the programming of a Mars probe, then the chances of a bug happening, even though it's relatively high, but the price that you pay for that bug happening is probably not too high. For instance, if you're writing a social media app, and occasionally the social media app would stop working. In other words, it would not give you the optimal suggested, post from your favorite people. And instead, it will just give you something that is ranked relatively low, on the list of things that you might want to read. Is that the end of Twitter? Is that the end of Facebook? No, not really. I mean, some people may notice that, hey, I'm getting some suggested reading that really does not interest me at all. But is it going to sink the company? Probably not the case. So there are a lot of programming situations where program verification is not really needed, even though it should be done. But if you're writing a driver, for an operating system, I would say in that case, verification really should be done, when in most cases people don't do it, because drivers also run at a high, let me try to see how to phrase it. It's running in protected mode, which means it has the same access to the hardware and also the operating system as the kernel of your operating system, the innermost portion of your operating system. Which also means if a driver, such as the driver for your USB mic, okay, if it fails, it can fail in a very catastrophic way. It doesn't just stop the mic from working, it can bring your entire operating system down. So just digressing a little bit to talk about why program verification is useful. But getting back to this, proof by induction is a very powerful proof technique, because every loop can turn into a recursive definition, and proof by induction works exceptionally well with everything that has a recursive definition. So that is important, right? So now we look at this theorem, and then we ask, so how do we use the technique of proof by induction? Proof by induction does not just work for the proof of the binomial theorem. It works for a lot of different things. Okay, if we have time, we can look at all the other examples. The first step of proof by induction is to establish what we call a base case. A base case is basically saying, let's take a look at this algorithm here. Okay, excuse me, let's take a look at this theorem, and the theorem itself is quantified. So instead of saying, okay, let's not be ambitious and say that this theorem is true for every single value of n, which is a natural number, let's focus on one. Okay, so we'll take one concrete example. And the thing about the proof by induction is you really can choose anything you want to. Okay, just pick a natural number, such as 4, such as 6, such as 17. Okay, you can pick one as your base, as your base case. But why do you pick all of those when you can pick 0, right? Because when you pick 0, this is pretty easy to prove. In other words, if I just want to show that this part here, p plus q to the power of n equals to this sigma notation, but only for the case when n equals to 0, that's trivial, okay? We like things that are trivial because they are easier. So you look at this and go like p plus q to the power of 0 is just 1, cool. And then on the other side, we have I going from 0 to 0, which means we have one iteration through this loop when I equals to 0. Then we have n choose 0. Anything choose 0 is 1. So n choose I is 1. P to the power of 0 is 1. Q to the power of 0, remember n is 0 to begin with, minus 0 is also just 0. So q to the power of 0 is 1. So we have 1 times 1 times 1, which is just 1. And that 1 is the only item that we have in the sigma notation. So that means we are just having 1 on this entire right-hand side. So we now have established 1 equals to 1. So that means the base case is done. Okay, we have no problem proving the base case when n equals to 0. What I just said is summarized over here. Okay, so that's it's just a summary of what we said earlier. So once we have a base case, then the next one is called the induction step. The induction step, okay, as it is stated here, the induction step is also quite interesting. The induction step has also two distinct steps or two distinct phases. The first one is we make an assumption. Now, this is true. It is just an assumption, but it's not just any assumption. This assumption is basically saying we assume that the theorem is true. In other words, in this case, we are assuming that this equality holds true for n being k. In other words, if I replace all of these n's here with k, it works. So you might be asking, so what is the value of k? That's the magical part. We don't care. We just say that for some k, that's a natural number, we already make the assumption that we know that p plus q to the power of k equals to the sigma of I going from 0 to k, and then the term inside the sigma is the same as what we see here, except this n is also k at this point. This n is also k at this point. So we just make an assumption. Then you go like, that doesn't feel right, okay? How can you just make an assumption with a k that is not even known, that's not even concrete? Well, that's the way proof by induction works. So the most important part here is this part here. Using the assumption that the theorem is true when n equals k, we need to use that assumption to prove that the theorem is also true when n equals to k plus 1. So the induction only can go one step at a time. So we cannot jump from n equals to k to n equals to k plus 6. It has to be the next available integer, a natural number in this case. So the assumption is going to give us this equality because we are basically just looking at the equality inside the quantification and expand it and replace, substitute n by k. So everywhere we saw n earlier, it is now replaced by k. So this is the assumption. Now, why do we make this equality here? Well, that's part of the proof, okay? Part of the proof is to make the assumption that it works for the case when n equals to k. So now we need to work on the case when n equals to k plus 1. So when n equals to k plus 1, then we are dealing with p plus q to the power of k plus 1. And we want to end up with this notation here, which is the same thing as this notation here, except n becomes k plus 1. So that's, this is where we start. This is where we want to end. And in between are all the steps, those are all the derivation steps. So yes, we are going to take this through, okay? I'm not going to skip over the proofs here because in CISP440, which is essentially a math class, the proofs are important, okay? So let's go ahead and go through this proof here. Yes, I just took a deep breath. All right, so p plus q to the power of k plus 1 is p plus q by itself times p plus q to the power of k. That seems to make sense, right? Because this power here that has the extra plus 1, that can be pulled out of the power notation by itself, and then the power notation can now take one step down from k plus 1 to k. Now that seems easy. But this is where we use the assumption, the induction assumption, is when we see p plus q to the power of k, we use the assumption and say, we can now re-express that as the sigma notation of I going from 0 to k, blah, 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 okay? I'm just putting this entire thing in place of p plus q to the power of k. And then what we do is we move the constant outside of the sigma into the term inside the sigma, okay? Because you can certainly do that. P plus q does not depend on I. As a result, you can always put it back into the expression that we are summing, using the sigma notation. From here to here, I do a distribution. So from one single sigma notation, now I end up with two sigma notations like this, where the first one is combining p to the power of I, q to the power of k minus I, with this extra p here. So this extra p is changing the power of p to I plus 1 instead of just I. On the other one, we basically have the extra q, and that is being added to q to the power of k minus I. As a result, we have q to the power of k minus I plus 1. So from this line to this line is just distribution, and we are also absorbing the extra term because of the distribution into the power expression that is already applicable to that particular term. When I talk about the term, we're talking about either P or Q in this case. From this to this is a little bit tricky, okay? Because what we are doing here is we are splitting each sigma notation into two parts. One part corresponds to either the beginning of the sigma or the end of the sigma, and then the other term is the rest of the sigma. So let's check this out, okay? So let's check out how we got this term here. Which sigma did we pull this extra term out of? So the way we identify that is we take a look at this is p to the power of 0 times q to the power of k plus 1. So this term cannot possibly be coming out of this because this one here has I starting from 0, but the first term is going to have p to the power of 0 plus 1, which is p to the power of 1. So this term here can only be peeled off from this sigma notation here. And because this one has p to the power of I, and in this case, we have p to the power of 0, that matches the case when I equal to 0, which means we are dealing with the first term of this sigma notation here. Then you go like, okay, so if I equal to 0, that explains why we have p to the power of 0, because this one has p to the power of I. It also explains why we have q to the power of k plus 1, because this one has q to the power of k minus I is 0, and then plus 1. So that explains the powers of p and q matching the powers of p and q over here when I equals to 0. And this I being 0 also explains this I being 0 here. What you might have a question about is why do we have k over here and this k plus 1? Well, that's because anything choose 0 is 1. It doesn't matter. So k choose 0 is 1. K plus 1 choose 0 is also 1. So I can express 1 in either way. So it doesn't matter whether I express that 1 as k choose I, or I express that 1 as k plus 1 choose 0, they work out in the end. But because I pull the first term out of this sigma in by itself into here, now I also have to remember to change the start index of I. Instead of 0, it is 1, because when I equal to 0, it is out by itself as its own term. So the rest is just this thing here. So if you look at the term being summed, it is identical to where it came from. The only change is I, instead of starting from 0, is now starting from 1. All right, so that explains the split. This term splits into one single term by itself and the remaining of the sigma notation. And now you can probably guess what happened to this term over here. Except in this case, I'm pulling the last term out. In other words, when I equal to k, which is the last term, I took that term out by itself into here. Let's check whether that makes sense or not. When I equals to k, then the power of p is going to be k plus 1. Oh, the power of p here is indeed k plus 1. When I equals to k, then q to the power of k minus I is q to the power of k minus k, which is q to the power of 0. That's how we end up with the q to the power of 0. And we have k over here. Excuse me, let me take it back here. I is k when we are at the last term, so we should end up with k choose k over here. So how did we end up with k plus 1 choose k plus 1? Once again, k choose k is 1. K plus 1 choose k plus 1 is also 1. Now, if you're asking why that is the case, you can just expand the k plus 1 choose k plus 1 using the definition of combination, and you will see why it is going to be 1. Okay, so this is all based on the definition of combination. So I can express 1 as k choose k. I can express 1 as k plus 1 choose k plus 1. They have the same effect. But because the last term is pulled out, so that means the sigma notation now can only go from 0 up to k minus 1, because when I equals to k, it is pulled out by itself as an independent term. So from this line to this line, what do we do? Well, what we did is this part over here. So I decide that of the two sigma notation, one is starting from 0 up to k minus 1, one is starting from 1 all the way up to k. So that means each one has k terms in it, but the start and the end are different. So I decide, let's see whether we can make them exactly the same. In other words, I can now look at this particular sigma notation and say, I want to change the index to start from 1 all the way up to k, instead of starting from 0 all the way up to k minus 1. So how many terms are we adding? We're still adding exactly k terms. But in order to make these two sigma notation to be the same, for every I see here, it has to be replaced with I minus 1 over here, because I starts at one value higher than what it used to. So I minus 1 is going to cancel out the effect of sliding the beginning and the end, and we just end up with the same term that we are adding at each position of the sigma notation. So everywhere I see I, it becomes I minus 1. Everywhere I see I, it becomes I minus 1, except in this case, because it's I minus 1 plus 1, so it's just I. Everywhere I see I, it becomes I minus 1, except in this case, because we're subtracting I. So when we subtract I minus 1 in parentheses from k, it is the same thing as I minus k minus I plus 1. That's the only change between these two lines. And then from this line down to this line here, I also make some changes by saying, hey, if these two sigma notation start from the same integer and they end with the same integer, then I can just go ahead and combine these two sigma into one, where it has two terms. The first term is this thing here. The second term would be this thing here, but they belong to the same sigma notation. But I also can do one simplification, because I can do factoring. Because if you look at what we are dealing with, is this one has p to the power of I times q to the power of I k minus I plus 1. Same thing over here. This also is p to the power of I times q to the power of k minus I plus 1. So I can do factoring. So this is where the factoring comes in. We have the power of p and q are singled out. And then we use factoring to basically have the two coefficients, k choose I minus 1 coming from here, k choose I coming from here, to be in its own addition, and then that sum is multiplied to the powers of p and q. So now we combined these two sigma notation into one. Now this is where we applied what we talked about earlier, which is known as Pascal's identity. So Pascal's identity, let's check it out here, all the way up here. So Pascal's identity basically say if you have n choose k plus n choose k minus 1 to begin with, you can end up with just n plus 1 choose k. So down here, we are applying exactly that, except we instead of k, instead of n, we have k over here. Instead of k in the previous one, we have I over here. So it's really just choose just the name of the variables being different, but it's the same pattern. So by using Pascal's identity, k choose I minus 1 plus k choose I becomes k plus 1 chooses I. That's how we combine these two into one over here. So when we look at this, okay, when we look at this entire thing, we just notice one thing, right? We are noticing that this pattern matches this pattern here when I equals to 0. We look at this pattern here and we say, hey, it matches this pattern over here when I equals to k plus 1. So now we roll this into the sigma, because it really is just when I equal to 0 in this sigma notation. And then we can roll this term into the sigma as well, because this term is really the same thing as this term here when I equals to k plus 1. So by extending the sigma notation to start from 0 And to end at k plus 1, we have one sigma notation again. But when you look at the sigma notation versus what we started off with, this is also just basically saying the theorem is holding true for the case of n equals to k plus 1, because the theorem that we are trying to prove is trying to say p plus q to the power of n is this sigma notation. So if n is k plus 1, that is exactly where we end up with p plus q to the power of k plus 1 equaling to this sigma notation. So basically this k plus 1, k plus 1, k plus 1 over here, they are basically taking the place of n in the theorem that we are trying to prove. So we have just concluded that based on the assumption that the theorem holds true for the case when n equals to k, I can use that assumption to prove that the theorem is also true when n equals to k plus 1, and that's it. This is the end of proof by induction. You have a base case, you make the assumption that it works for the case when n equals to k, you use that assumption to prove that the theorem is true when n equals to k plus 1, and that's it. Okay, this is the power of proof by induction, is you just start with a base case, which is usually trivial to prove, and then you just have to use the assumption to help you move on to the next step. All right, so now we have just proven the binomial theorem, and some of you are now looking at this and go like, okay, hold on a second here. We know something else about Pascal, right? Because we have Pascal's triangle. So for those of you who don't know about Pascal's triangle, let me illustrate it using the spreadsheet. So we just go ahead and add another sheet to the spreadsheet here. So Pascal's triangle is trying to figure out the coefficient of the terms. So I am going to specify rows and columns have special meanings now. So if we are to talk about n being 0, okay, and we are talking about k being 0, then the coefficient of that thing is 1. Okay, so there's 1 of q to the power of 0 times q to the power of 0 when we are looking at p plus q to the power of 0. All right, so this n and this k here is corresponding to, let me get back to the module. I'm going to get rid of the stuff that is unnecessary, so this way I don't have to search for the things that is relevant. Okay, so there we go. So n and k are referring to these n and k, which in the end ends up being the n and the I over here instead of k. So, sorry. So getting back to the spreadsheet. So when n equals to 1, we are looking at p plus q to the power of 1. And then we can look at the case when k equal to 0, which means we are looking at q to the power of 1. So there's one of those. And then we can look at the case when k equals to 1, which means we have p to the power of 1, and there are one of those too. When n equals to 2, we have when k equals to 0, that means we're looking at q to the power of 2. There's one of those. When k equals to 1, we are looking at the case when we have p times q, and there are 2 of those. And when k equals to 2, we are looking at the case when we have p squared, and there's one of those too. So what we notice is what Pascal's triangle is about is this number is the summation of these two numbers. But if a number is at the edge of the whole thing, then it is 1. Same with this one over here. So when we look at n equals to 3, we look at this one. This is at an edge. It is just 1. This one is not at an edge, so it becomes this number plus this number here. So this is 3. This number is also not at an edge, so it is just this number plus this number, which is also 3, which means it is just 1. So this corresponds to k equal to 3. So now, and when we extend it to k n equals to 4, this is at an edge. This one is not at an edge. So we just deal with the two edges first, like this. And then this one becomes just the summation of these two, which is a 4. This one becomes the summation of these two, which is a 6. This one becomes the summation of these two, which is a 4 again. And then when n equals 5, then the edges will be from here all the way to here. This term becomes the summation of these two, which is a 5. This one is the summation of these two, which is a 10. Summation of these two, which is a 10 again. And the summation of these two, which is a 5. So this is Pascal's triangle. It is useful to figure out the coefficients of each term when you expand a binomial expression. And as you can see, this is really just making use of what we said earlier. This is k equal to 4, and this is k equal to 5. So the Pascal's identity is really just the boring expression of what we also know as Pascal's triangle. So that's how you can relate the probability stuff that we are talking about in this class to something that you already know in algebra, which is what do you get when you expand a binomial power expression. I'm just looking at the time here. It is 9 o'clock. This is actually all that I covered in 80 minutes, in the failed attempt of recording this lecture. Excuse me. The second time I can get through this stuff a lot faster, just because the first time I was actually stumbling through some of the derivation, but the second time through, you're going through this explanation here, I'm not stumbling through. I know exactly what I'm talking about. Well, I mean, I did do this derivation, but that was years ago. You can look it up. The last time I touched this was April 18th in 2022, which is almost exactly a year ago, off by maybe a week or so. But basically, I cannot remember this entire proof. So the first time I went through this last night, I was stumbling through some of the steps, and this time, because it's the second time I'm going through this, on the second day, I just kind of breezed through the proof itself in the explanation, and that kind of saved some time. So I'm going to stop here because this stuff is dense, okay? If you are to understand the proof by induction by itself, it is a little complicated. It takes a little bit of time to really understand what is the basis, what is the base case, what is the induction step. In the induction step, what is the assumption? How do we make use of the assumption in the induction step? Those are all the really critical ideas that we need to talk about. But I can show you additional examples when we get back on next Wednesday, because next Monday is when we're going to take exam 2. So we'll continue on this discussion on next Wednesday, which is 1 week from today. Today is the 12th. So on the 19th, we are going to pick up from where we left off today and continue with all of this discussion. All right, so I'm going to end the recording now so that I can upload it probably within 15 minutes or so. All right, I look forward to seeing all of you on Monday in the exam, and then also next Wednesday as a continuation of these topics. Have a nice weekend.